simple example. We have a shape fixed to the wall. The dimensions are given, component is given. We have only one source of loading, and that's the component in the middle of the beam. And the question is asking, find the maximum and minimum stress in this following configuration. So, based on what I have studied so far, I studied kind of normal stress, which was either coming from the axial load. Do I have axial load here? No. Or from the bending moment. The one that comes from the axial load is uniform, either tension or compression. The one from the bending moment is somewhere in the beam is tension, somewhere in the beam is compression. It depends on the sum of moments. So far we have studied this. Also, we have studied the shear stress very briefly. And here, absolutely, we don't have any shear load. And the concept of shear, after we cover this bending, we go to the shear load, more detail, and we find the Hooke's law for shear, which is very similar to Hooke's law for the axial load, right? The normal stress. That's called shear stress. And also, then we go to a concept called torsion that is related to shear. Right, so instead of following by the classification of the book, I decided to first cover the normal stresses, and then once we're done, we go to shear stress, resulting to bending. So here we know that only we have a couple moment, and the stress comes from the pure bending, and so therefore I only need to study the bending. For the bending, the equation was sigma is equal to mc over I. We write this equation in detail last class. In general, the equation is m over I times y. And that's for the cross section. Let's say this is your cross section. And then you have your centroid. So I show the centroid with this symbol. And axis passes through the centroid. Let's call it, for example, Z. Let's call this axis DZ. Therefore, this is I, DZ. So for any arbitrary cross-section, you have to first find the centroid and pass the axis through the centroid, and then find the moment of inertia transfer to the centroid. You remember we did vectorostatics? When we wanted to find moment of inertia about the particular axis, we had to transfer each individual moment of inertia with respect to its local centroid to the global centroid. So that I is coming from here. M is the bending moment at that particular section. And Y is the distance with respect to the centroid. So this is Y plus, and this is Y minus. The distance from the centroid. It's not the distance from bottom or top, it's distance from centroid. Up is positive, down is negative. And convention is, when you have bending moment that causes bending to curvature up, it's positive. The bending moment that causes curvature down, I mean the convexity, is negative. So we know all these things. So what I'm trying to get is my stress out of the equation. So if I want to compute the stress using that particular equation, what do I need to compute? I need to compute the moment of inertia and the bending moment diagram. So in your book, it uses the bending moment diagram to a very late chapter, so we already covered that. We covered the axial load diagram, bending diagram, shear diagram, very detailed. We'll have more examples. So the first thing I'll do, I say, well, let's compute this bending moment diagram, and then I compute the moment of inertia. So if I want to do that, again, I need to find the external reactions. So I take the entire thing as system. There is a, let's say, point A, B, C. There is a reaction at MA. I know that because I don't have anything in X, any force in X or Y, I don't really bother to put AX and AY. But I know that there are zero from summation of force in X, Y, 0. So you get MA and B, you already have 2K, and nothing at C. So therefore, by just writing one moment between them, I get MA is equal to 2K. That means that here, there is a 2K on the wheel, on the system. Alright? From the diagram, it looks like something like this. And I'm drawing one diagram. Why? Just a bending moment diagram. Why? Because that's what I want. You see over there, I didn't ask for the shear diagram. I asked for the bending moment diagram. Okay, you need moment. Also, you can take the derivative of that and find shear force. So therefore, I just do one diagram. So here, let's take your X. How many intervals should I consider? 2. From here to here, from here to here. So if I cut it, X from here to somewhere here, X, for X between 0 and 1, I do get here and mx. Then mx is mx plus 2k is equal to 0. Mx is equal to negative 2 kilonewton meter. So from here to here, you have negative 2k. Now what about from here to here? 0. It's 0. Why? Because I know that if I take the right part, what do I get? It's just suspended in the space. So everything is 0. Moment, shear, axial load. So immediately you don't do that again. You say the same here from here to here. 0. So that's your bending moment diagram. So what else? The moment of inertia. Moment of inertia for that, that's exactly. So this is your cross section. I can do like this way. You can do it in a variety of different ways. You can, what I do is I cut it into A1, A2, A3, A4. What else can I do?
You could take the inertia of the smaller sphere and subtract it from the inertia of the larger sphere.
That's one way you can do it. In fact, I was going to post this as say just like a meter wave or quiz wave or what, I'm glad I did it. The most obvious thing is, what can you do? First of all, do I need to compute the center? The first thing you need to compute the center. That's the problem we have in the mechanics of material lab. Students compute the moment of inertia with respect to the base. And then they put it in that equation in the lab and they see that they have like 2,000% error. And then we realize, well, the problem is, first we shoot for the dimensions. And then I realized the dimension by gigapascal, that's 39. That's usually 99% of the problem. Gigapascal is not 36, it's 39. The next problem is, you find this moment of inertia with respect to run coordinate. You have to find the respective centroids. So in this case, so I need to find the centroid. It's perfectly symmetric, so it's right here. So if my axis is right here, let's say this is your ZZ, axis Z, Z. Then my IZ is extremely easy. If I do IZ is equal to IZZ is equal to IZZ field minus IZZ empty. So you can consider that, one way to do that is to consider the big thing and the field and this one empty, because it's empty. When you add the IZZ, you put a negative sign, so it's empty. And the big one is positive. This is the best way, because you don't want to compute the center. The center from the symmetry is exactly in the middle. Now, if you had, like we have in the next example, an example that you don't have symmetry. In that case, it's better to cut it down into sub-areas, compute the moment of inertia of each with respect to its local axis, and then transfer it to the global. That's what you can do as a homework. Cut it up into A1, A2, A3, A4, and do that. You must get exactly the same result you get here. What is the other way to compute the moment of inertia? We have considered two different ways. Yeah, you can say, well, you know what, because it's complete symmetry, the top is equal to the bottom, right? So you say, you just eliminate this bottom, right? And say the moment of inertia is twice the moment of inertia of top. Another way is you can cut it like that. A1, A2, A3, A4, A5. But that's going to be a little bit lengthier. But the result should be the same. So I strongly recommend, if you want to learn this concept of moment of inertia, please go ahead and do it different way. Do not just memorize that. Do it in different ways. So here I'll go to the table again in the book. Let's do it here. For solid field rectangle AB, I is equal to 112 A E cubed. Therefore, that means that I field is 112 A. So this one, A is from here to here is 2, and this is half here, so the entire thing is 3. The smaller one though is 2 centimeters, 3. And we have the same thing here. So this is 2, I have 3, and 2 here. Right? So 112, 3, 10 to the negative 2, 2, 3, 10 to the negative 2, 2, minus 112. Now the smaller one, the empty one, is 2, 10 to the negative 2, times 2, 10 to the negative 2, cubed. Put in the calculator. times ten to negative 9. 54 times 10 to negative 9. Alright, so this is in meter. So don't forget, another thing that we have big source of problem is the dimension conversion. So usually students, for example, don't forget, they forget to put this 10 to negative 2 here, and then the end result is centimeter to the fourth power. And then they say, well, centimeter to meter multiplied by 10 to negative 2. And don't forget, centimeter, this is the fourth power. It's not just centimeter to meter conversion. So you have to multiply by a very small factor, conversion factor. So the way I do it, I put the conversion factor here. You could just factor out this 10 to negative 6 out, the mega. 1 over mega. You could exactly that. So that's the end result. IGZ is that. Now I have everything to find the maximum and minimum stress in the following way. Well, if we talk about the magnitude, if you say, well, in the sense of absolute value of sigma, where is the minimum absolute value of the stress? Yeah, it's right here, BTC, 0, the absolute value. But in this case, we want to find maximum positive and minimum, meaning the negative number and the location where it happens. Because we know that it's going to we're going to have a different value. Like in even one section, we're going to have a different value of the stress. We talked about the linear distribution, the line that's through the central, the neutral axis. So we have to explain it exactly. So I consider this section from A to B, and I know that the magnitude of the stress is, so I use this formula. I use this formula. I say sigma is equal to, it's right here, sigma is equal to the bending moment, which is 2K, its magnitude, the same magnitude of sigma, max, is equal to 2K, which is 2 10 to 3. Again, another thing we have, when they put 2K in the equation, they forget to, when they put in a calculator, they forget to say 2 times 10 to negative 3. So when we have K here, that's the 10 to negative 3 right here. 10 to negative 3. So 2K times 10 to negative 3, that's what M. What do I put for I? 54.2 10 to negative 9 times C. So where is C? C is the maximum deviation from the neutral axis. The neutral line of neutral axis is right here. So what point is maximum deviation from that? Either top or bottom. So it's going to be half of this, which is 1.5. So you multiply by 1.5. What am I missing? Trying to 10 to negative 2. Because that's centimeter, you have to convert to meter. Now this is completely ready for you to put it in a calculator and get the value in Pascal. The value is in Pascal because everything is meter, Newton, it's in the SI unit. So 2 P3 times 1.5 e negative 2 divided by 54.2 negative 9. Then you get 553 4 mega Pascal. 554 megapascal. Sigma max. Now I want to draw this on the limb. that at what location this particular stress happens. So you know that here, because I'm bending moment this way, this is going to go nose down, right? So in the top is tension, in the bottom is compression. So if you draw this beam right here, like that, the deflected beam is going to look like this way. Let's do a little look at the elevations here. There you go. Scaling. The deflected beam will look like now if we have time at the end of the semester we will talk about deflection too. But this point is not going to deflect, has any deflection. It's not going to go. Why? Because it's fixed in the wall. But everything else will go. Now you can clearly see that at this point you have, at this particular point, you have tension. Right? Yeah. And this point after the middle is straight. Here, the deflection, like that. And these points are compression. So when I have the tension here, what is my stress here from here to here at this point? 500. So if I want to draw it, it's going to look like this stress distribution. The maximum, the peak is 554 MPa, and then it goes, excuse me, the center it goes to linearly goes to 0. It's the neutral axis. What was the definition of neutral axis? When you have the stress is equal to 0. And then it goes to negative. So in this one, you have the same value. All is negative 554 MPa because it's symmetric. So the top, max, and mean are identical because it is symmetric. If they are not identical, if it's not symmetric, then you centrally shift either up or down, right? And then the max is not necessarily identical to mean. Then you have to find max and mean separately. Here the max and mean are the same. So that becomes your cross section. This is called cross section of the stress diagram because it's paired cross section. You see that? Now if I draw this cross section of the stress diagram in different cuts from here to here, if I do different cuts, what do I get? Exactly the same diagram. What do I get here if I cut it? The cross-sectional shear stress diagram, bending stress diagram. What do I get? Just 0. After from B to C, you don't have any bending stress. But just before that, the diagram would look like that everywhere. Okay? Example number 2. This could be for example, a question in the final exam. Again, we have the same situation. Find maximum and minimum bending stress. We're talking about that. Find the maximum and minimum of that. In this case, let's say we have a different cross section. Let's say the cross section is circular. Find the maximum minimum stress. Let's say the cross section everywhere is diameter 2 centimeter. Solid circle. Okay. So what should I do? Bending moment diagram. So I just come. But before I do that, I want to talk about another important mistakes. Usually many people do that. They say, well, this is one beam. They don't consider this is beam. Two different beams together at this point. See? No friction, pinned together. They say, well, this is one beam, and then they come and draw a figure like that. And then they say, well, here you have, let's say this point A, B, C. A, B, C. A, Y, A, X. Then they say C, Y, 5K, 2K. Here's another source of problem we have for the students that don't practice at home. They say, well, if he gives a solution like that, because they memorize what I said, he said in class that if you get a beam like that, you put it like there, and then solve it. And that's completely wrong. Why? This is assuming you say, well, I take the entire thing as system. Okay. Take the entire thing as system. How many reactions do I have here? AX, AY. How many reactions I have here? This is not a roller. This is again infinite. Again 2. CY, CX. And then I will have 2K and 5K. Bending moment and. Now the question is, how many equations do I have for that one system? 3, right? Summation of force in x0, summation of force in y0, summation of moment 0. How many unknowns do I have? 4. Can I solve it? No. So when they reach the point, they say, well, you know what, I can forget this CX. And then they solve it, and they go, everything is correct, but the result is not correct. The bending diagram is not correct. It makes a big mess. Please do not do that, because this is two different beams. So what should I do then? Consider each one as a system. So then you reiterate. You go back to system. So I take this as one system, and this one, and my system 2. So I draw my FPDs, system 1, system 2, then I have AX, AY, AY, AX, 2K, and then you can introduce BX and BY. Once you do that, then you just put opposite of BY here, and BX going this way, 5K, and then CX, CY. Then when they do that, they kind of freak out. They say, well, we even make it worse, because now I have 2 extra. But you tell me, how many systems do I have? How many equations per system? 2 times 3, So the number of total equation is 6. What is the number of total unknowns? Who said 4? It's 1, 2, 3, 4, 3, 4, 5, 6. Now you have 6 equations, 6 unknown. Can you solve it? Yes. So why do we do that? Why do we do that?
Because we need to see if it's undeterminable. Because if it
Yeah.
is, then you don't have to solve it.
Yeah. Another thing is, well, I'm trying to solve this problem to get sigma, and if you want to solve that, you have to be able to draw bending moment diagram. When can you draw bending moment diagram? When you have exactly the reaction forces. So you can cut it and draw that bending moment diagram. That's the reason I'm doing all these things. So if I give a question like that in the exam, please try to follow the steps. So again, let's go back to solving problem. CXY, 1K, everything included. So for this system, let's say system 1 is good. All right, the equation. So first, summation of force in X, 0, we get AX plus BX, 0, summation of force in Y, 0. And you get AY, negative 2K, plus BY, 0. Summation of moments at any point is equal to 0. What point should I consider? A. If you consider B, again you eliminate 2 unknowns, but you will lose the connection between 2 systems. So for A, you get BY, 2K times 1 with a negative sign, plus BY times 2 with a positive sign is equal to 0. So these are equations for system 1, system 2. Again, you have negative bx plus cx, 0. You have negative by plus cy is equal to 0. And summation of them over any point I take c. Therefore, you take negative 5k plus by times this distance, which is 1, negative 5k plus by times 1 is equal to 0. What equation should I solve first? Either hold on. Yeah, the thing is here we have some sort of inconsistency. If we solve, By here, that's interesting. If we solve By from this, I wrote moment equation at that point, so we get negative 5k plus By times 1 is equal to, if you solve By, you get 5k from here. And if you solve dy from here, which I wrote the moment equation with that, then you get what? You get 2 times 1 negative plus by times 2 is equal to 0. So you get by is equal to 1k, right? So that's kind of like inconsistency because by should be exactly equal. By here is equal to 1k. And by is equal to 5k. And you know the thing is, we should not have an inconsistency like that because by is 1 point and they should be equal to each other. So I'm trying to figure out what we can. That means that this system cannot be in equilibrium.
What's the second? What's the distance? Where are we? We're going from C, the moment around C. So the 5K.
That is correct. That is correct. So this, what does it mean? If I get that, what do I get? That means this system cannot be in equilibrium. It's impossible. That means it will move, right? So we have to stabilize it somehow. So one way to stabilize is this dimension. I say, well, is 0.5, right? You can extend that such that, let's say this dimension is 1, it is x. Let's say from here to here is x, from here to here is x, right? Therefore, if I do the x, right, the moment I do it from this plane, then I get negative 5k plus Vy times 2x, right? Then in that case, I say, well, here Vy is 1, right? And then I put it here, and then I get x is equal to negative 5k plus Vy is 1k times 2x. Then for the particular value of x, the system is stable. So you get 2k times x is equal to 5k. Then x is equal to 2.5 meter. 5 divided by 2, 2.5 meter. So instead of 1 meter, 0.5 meter, add a 2 here to make it stable. So 2.5 meter here, 2.5. So I have that. Then I can go ahead and solve for the rest. Right? So what else can I solve? If I get Vy, then I can get Ay. So Ay is equal to 2k minus Vy is equal to 2k minus 1k is equal to 1k. Ay is equal to 1k. So Vy, Ay, Cy is equal to, solve this equation. Cy is equal to Vy, which is equal to 1k. And that distance is 2.1. Alright? So I kind of know my things in the y, so I can already, so here Ay is equal to 1k. If you separate this plane into this way, 2k, 1k, and here Vy positive 1k, and this system over 2, 1k down, and 5k, and Cy is equal to 1k. Alright? So that's my problem that I have here. These are the distribution of the force and moment. Now I want to draw my diagram. So let's get rid of this computation here. Again, how many intervals should I consider here? 4. You see, this pin can be source of all sorts of troubles here. You usually don't see it. But that pin exists, that means we separate two systems. You see, I have 1k here, and I need to consider. So then I can say, well, I have 4 intervals instead of 2. I have 4 intervals from here to here, from here to here, from here to here, and then from here to here. So if I cut it here, x, Then I draw a family. I know I have 1K at point A, and that's point X, MX. Forget about V and normal. We just interested in everywhere, right? So if I write moment equation at that point, I get MX positive, negative 1K times X is equal to 0. So the moment is equal to 1K times X. So let's go ahead and write. Let's do the diagram like that. X, MX, moment at X. And from here to here is positive 1K. How many points do I need to draw that line? 2. Moment at 0 is equal to? 0. Moment at 1 is equal to 1K. So let's say this is good. 1K. So you have 1K times X. Positive. Now, I go from here to here. This distance. Then you have, continue this cut. Then you have something like that. Here you have a 2K. From here to here is 1 meter. And from here, the point that you cut is X. Look, my reference for X is same. I'll just take it to the right. Right? 2K1, that's X, 1K, and you're going to get MX. Again, do the same thing, summation of moments about this point X 0. So you get positive MX plus 2K times X minus 1 negative 1K times X is equal to 0. What did I do? I wrote summation of moment what? This one is 0. MX is already positive, plus the moment comes from 2K. What's the moment come from 2K? 4 times the moment arc. So 2K, which is 4 times the moment arc. Moment arc is from the reference point to the point that force is acting on. What is from here to here? X minus 1. It's not X, it's X minus 1. That's the reason you see X minus 1 here. Then you go to this point. What's the moment come from this force? Force times moment arm. Moment arm is from here to here. What is from here to here? X. Right? So that's the reason I have negative 1 to come X, because it's 0. So here, expand that, you get 2K times X minus 2K minus 1K times X. So then you get 2Kx minus 1Kx is 1Kx minus 2K plus moment plus 1Kx minus 2K is equal to 0. Take everything to the right. Then the moment of X is equal to negative 1Kx plus 2K. That's the moment solution. Now I want to write. How many points again? 2. If it was a second order term, plus x squared, how many points did you want? 3. If it was cubic term, how many points? 4. So in fact, the number of points you want is the power of x plus 1. I mean, I'm talking about information. You may have points or have point and a slope. Right? A slope and a point. If you know the slope also, that's information. So for that, you need two information. Two information, one at here, one at here. What's the value of bending moment at x is equal to 1? 1K, right here. And the bending moment at x is equal to 2. 0. Then you put it here. There you go. And then this curve is equal to negative 1Kx plus 2K. and here is 0. Now I go from point B to this point. So I continue my x. You know what, I can just consider now for this part, my x I can put it right here. Right? You diagonal will look like the same. So I put my x here and then I cut it. So I say I cut it from here to here and then I cut it from here to here. So if I cut it from there, then I get let's call this x bar. Right? X was in this coordinate system, now I have in this coordinate system. You see that? I have a different y axis. So x bar, mx bar, forget about v and n here, and here you have 1k going down. 1k, no bending moment. Why no bending moment here? Because this is frictionless pin. You can easily rotate. Right? Because you have 1k that you have to consider. X bar, mx bar, and no axial load. So we write summation of moments of what? Point x bar is point x bar. Right here. Is equal to 0. I will give you mx bar positive plus 1k times x bar is equal to 0. Then mx bar is equal to negative 1k times x bar. So now I want to draw that. Interesting thing here, because I took my x bar from here, right? What should I put for this point? 0. X bar 0, what do I get? 0. So the bending moment is 0. And then at point 2.5 meter, what do I get? Negative 1k times 2.5. So it's negative. So it goes down a little bit more like that. And this value is equal to negative 2.5k. Right? And this value is equal to positive 1k. Now I want to draw the same thing from here to here. You see that? I want to draw the bending moment from here to here. What do I do? You can either take the left or the right. I'll take the one on the right. So from here, what is from here to here? You take the one on the right. From here to here is what? No, it's x bar. From here to here is x bar. Now if I continue to go to here, from here to here is what? X bar. So from here to here is what? 5 minus x bar. Then you have 1k. And then you have nothing else except mx bar, and forget about this. So then you get mx bar with the sign negative summation of mode over this point. So negative mx bar plus 1k times 5 minus x bar is equal to 0. That means mx bar is equal to 1k times, so negative 1k x bar plus 5k. Alright? It goes, yeah, another thing is because this goes to the right, we just use that. Right, so mx bar is equal to negative 1k x bar plus 5k. But this already negative, goes to the right, so we just use that, expand that, right? So I want to draw it, again, 2 points. Put x bar is equal to 5. What do we get? 5 is x bar because it's located from here. If we put 5, we go all the way. You see this 2.5 plus 2.5, 5. All the way to the end. You see that? So if you put x bar is equal to 5, what do we get? 0. So the bending moment is 0. Now put x bar is equal to 0. What do we get? Put x bar is equal to 2.5, which is here. Positive 2.5. So you have here a jump, because you see you have a bending moment. So you have a jump in the moment diagram. Right? So then you have this point. So positive, negative. Now if you had a shear load, you have jump in shear diagram. You see? The shear load, you have jump in shear diagram. You have you have jump in a moment diagram. Now if I give this to you and I say draw the shear diagram, what do? Take the derivative. Huh? Take the derivative. If you take the derivative of this, what do you get? From here to here is what? Is 1. So let's write here. Yeah, I know you guys are tired. I'm tired too. So from here to here is plus 1. So this is shear. Shear. Right? Shear diagram. Is the derivative of any moment. So from here to here is 1. What is from here to here? Again, the derivative. Negative 1. Do you see that? You have a jump in the shear diagram. Why? Because you have shear load. So if you have shear load, you will have jump in the shear diagram. But the moment diagram is continuous. Don't forget that. Now if you have bending moment, you have jump in the moment diagram. You can see that. So let's go ahead and now, because I know my values, this is negative 2.5, and therefore this is positive 2.5. Okay. Now, but just looking at your moment diagram, what are your critical points? Yeah, this point. This point is the one that causes the problem. Because you bend the moment to reach to positive 2.5, and just immediately before that point, you have negative 2.5. Immediately after that, you have positive 2.5. Now, I asked one question. Can you apply this relation? Can you apply that to the point, this point, exactly that point? That point is like you have a screw, there is a screw here, and you have a screwdriver, and you try to fasten it, right? You apply bending moment. Now the question is this equation valid in that point? Exactly. Now you talk about mathematical exactness. No. Why? Because that point, you remember we had the assumption of uniformity, like the stress should be like that. Let's say this is your specimen. You put it in the tension. Let's say we have a tension specimen. You want to do tension in the lab, right? And you put it in the machine, and you apply tension until you break it. Some of you guys have already done this lab, MLA, against material lab. That relation, the Hooke's law, this comes from the Hooke's law. You remember I applied the Hooke's law and integrated to get this equation, right? So the Hooke's law is only valid in the regions of uniformity, like that. In the middle, it's not valid here. Area change is not valid near this point. This point This point hold is a stress concentration. Hooke's law is not valid there. That means that when I have singularity like that, area change, hold, Hooke's law is not valid. That formula is valid here. That means that this formula is not valid because this comes from the Hooke's law. That's the reason I say you have to meet the derivation of this. You have to mathematically prove it to understand when you can apply that. Now, when you go to graduate school, they talk about the stress concentration factor for this point and this point, and you get confused. If you don't draw these things, you say, well, I know that the stress is not that, or it's just simply sigma is equal to E epsilon, the axial, the normal stress. So why are they talking about stress concentration factor? What is that? And then you get lost. That's because this equation comes from the Hooke's law, which is this, and this is only valid in the uniform region, not singularity, not area change, not hold. Therefore, you use the stress concentration factor here. Now, look at this point. What is that point? That point is like a hole that you have a screw and you have a screwdriver and you try to fasten it. You apply extra bending moment. So this equation that we draw here, this equation is not valid exactly at this point. Singularity. Right? Okay, so now let's go ahead and plug the number in the equation. The equation says the value of the stress is equal to magnitude of sigma is equal to m to the maximum 2.5 k 10 to the 10 to the power 3 over I. Moment of inertia. For the second, you go to the table in the book, in appendix P, I think. Then you have this information. Let's say this is XX, YY, and the book says IXX is equal to pi over 4. Radius to the force power, say this is radius, and IY, y is equal to pi over 4, radius to the force power, and then it's talking about something called IDZ, or polar moment of inertia. That's what we consider when we teach you the shear stresses. We have shear stress, and then something comes from direct conclusion of shear, it's called torsion stress. Right? That's for the next section. Here is called pi over 2. R force power. So which one should I use? This one, or this one? Which one should I use? Should I say nature very well found? If I don't say that, you're a good business people. You don't do anything unless you get a payment for that. Like, no contribution, zero contribution, unless I do something like, hey, if you can say, if you can repeat this formula, I'm going to give you a fine on this. That's just completely unfair. But it's right here. But which one should I use? IZZ, look, this is x-axis, and this is y-axis. And z-axis is like that. So IZZ is the one that you must not use here.
IXX.
IXX. Why? Because look, those are the beams, right? If you extend that like that, that's the cross section. Where is your loading? The loading is either this way, or this way. So every time you have a rotation of 2 is above x-axis. So that's the reason you should put IXX. You put IZZ, this is z-axis in 3D. When you have some phenomenon about that axis, kind of rotation, you call it torsion. Later we talk about that. We haven't heard it yet. So we have to have shear modular length. Suppose it's going to be very similar to this equation like that.
What would be the difference in IXX and IYY?
Well, because it's symmetric, it doesn't make any difference if they IXX or IYY. In this case, same, right? but you must not take RGZ, because that's obviously different. And from the vector statics, we have RGZ is equal to Ixx plus Iyy. That means that, you see, you add it together, you get this. But this is for torsion. This is for the time that you have bending, the moment that causes torsion like that. You see, like this. You twist it like that, right? What we have is bend moment. So here I put pi over 4 instead of I put pi over 4. The radius, which is 1 10 to the negative 2, 4. In the fourth order. Okay? Times C. And what is that C here? That's the maximum distance from the neutral axis. So again, because it's symmetric, both of them is what? The maximum distance from the neutral axis.
Just the radius.
Positive radius, negative radius. Right? From the neutral axis, you go one radius up, one radius down. So here, what should I put? No, I'm talking about this C. I'm talking about this. What should I put for C? Thank you. The radius. That's it. Put in a calculator. So that's what you get. Now, you can see that will happen right here. And it's what, when you do it on the right side of that point, because the moment is positive, that means on the right, you have bending upward. That means the top here is going to compress to that amount, and the bottom here is going to extend to that amount. Now on the left, you have bending moment down. That means you're going this way. That means that on the top, you're going to have negative compression. Sorry, here you have negative compression. On the top, you have positive tension. So the sides are like that. That point is kind of like singular phenomena. So now I want to talk about superposition. The midterm waiver proved that this is a midterm waiver. I think you can do that. Let's say you have a beam and two different forces. F1, F2. Let's say the length is L, cross-sectional area is A. Let's do it this way, AE, modular of reciprocity is E. Superposition principle says superposition. Deflection. Caused by total force or resultant force by the resultant force, call it F resultant is equal to F1 plus F2 is equal to the sum of each reflections if each force is applied individually. So this is a very interesting principle. There is an assumption for that. The assumption is good material should behave like linear. So the assumption of superposition, linear equations at a small deformation. So when you have these two assumptions, and let me tell you, we will have these two assumptions everywhere in this course. Our equations are always linear, and our equations are, our deformation is very small. You remember our usual drive 10 to the negative 6 micrometer. So it's very small. Deformation, the string is very small. So based on that assumption, I can say if you have a sum of forces, for example, here just say 2. The deflection caused by two forces is equal to sum of algebraic sum of the deflection if each force was applied individually, independently. That means that, for example, here, instead of considering this complicated phenomena, you could consider the same thing that you have only F1, so you could analyze F1, the deflection, and add the effect in the case that you only have F2. And that value is equal to if you consider both of them simultaneously. So if you prove that, then only have 1 minute, then you get a meter wave. Can you do that? Mathematical proof. You just say, well, you know, I think that makes sense, it's intuitive, but how can you show it mathematically? Yeah, yes, please, here. Opportunities are available for waivers, midterm waivers, final waivers. You gotta participate somehow. Excellent. That's the formula we drive when we study pure normal stress, not bending. The deflection was equal to F over E AE. It comes from the Hooke's law. You want to do that? Yes. Yes, that's right. That's right. Yeah, even. Yeah. That's right. Yeah. 1, 2. That's right. 3, 4, 5. Email me. Well, I can only Ariel you maybe I'm sorry, he just wrote it and everybody like, hey, here. I know you did it. I know you did it, but we will have more opportunities. Don't worry about that. 1, 2, 3, and 4. Not talking enough, I wish I could go this way. But email me, thank you. So the way he did it, he said the resultant force is sum of two forces, right? That dial is that. So if you find that deflection comes from the resultant force, you put resultant force. And then this method, and what is that? Deflection from force one individually plus deflection from second force individually. Now, if the equation was nonlinear, that means, you see these are constant time force, is linear. If the equation was nonlinear, you cannot easily expand it like that. You get some, you see, if you have a plus b squared, then you have a squared plus b squared plus 2ab. Then you have extra terms. So that's the reason I say linear equation. So we use superposition to get maximum stress next class.